All right, welcome back to the C++ course. This is chapter 18, linked lists. If my math is correct, this is the third to last chapter of the course. So we can see the end in sight. We're going to wrap up the course with some lessons on some specific types of data structures. Linked lists is going to be the first one. It's what I would say to be the most versatile data structure. And we're going to take the approach of we're going to sort of create our own linked list implementation. It's a very, very good sort of learning tool to see how these things are created from scratch. And then it's actually something that could potentially be useful for you. You could take to any different project that may need some linked list functionality. So we're going to take a look at linked lists in general, kind of what they are, what some of their properties are, why they're useful. We're going to take a look at some of their operations. What can they do once they're created? Because a data structure is a collection of data and also operations upon that data. And we're going to create a linked list implementation that utilizes templates. So we'll be allowed to store things inside of our linked lists other than just integers or doubles or just kind of these primitive data types. We'll be able to store whatever we want inside of our linked lists. Take a look at recursion, throw back to a previous chapter, and how it applies to linked list operations. And we'll take a look at some variations of the linked list. And then we'll take a peek at how the STL, Standard Template Library, handles a list implementation, including the forward list container. So intro to linked lists. This is kind of the classic image or graphic that is used to show kind of what a linked list structure looks like, how it's laid out. Basically, it's a series of dynamically allocated data structures called nodes, with each node containing a pointer to its successor, or to its next node, basically. The last node in the list has its successor point to null PTR. And typically, we maintain a record of basically what is the front or what is the head of the linked list. So it exists out here. It points to its next node. Then that node points to its next, points to its next. Yes, we use the word pointer, so there are pointers involved in our linked list data structure. But it's not just a bunch of pointers to nodes. That would be kind of a useless structure. We actually need to store information inside of our nodes, and that's kind of where this big empty box comes into play. That is a space where we're going to store whatever type of data we've specified from our template is going to go in here. So we could think of a node as sort of a pointer to the next node, as well as whatever data you want to store inside of the nodes. Some terminology. So the beginning node is called the head of the list. The entire list is identified by the pointer to the head node. The pointer is called the list head. So when we refer to a linked list, like an instance of a linked list, we're really referring to a pointer to the head node. Nodes can be added or removed from the linked list during execution. Addition or removal can take place at the beginning, end, or middle of the list. And this is why we say that linked lists typically are very, very flexible data structures. It should also be noted that the memory that we use to allocate our linked list and any given node inside of it could be, there's no telling where it might be in our computer's memory bank. If you remember back to the arrays chapter, we sort of said that arrays occupy a continuous set of memory inside of our computer. And that's part of the reason why they were so fast, is because the data existed right next to other data in the array in our computer's memory. It's not necessarily true with a linked list node, however. The nodes could be scattered about in our computer's memory, really with no particular rhyme or reason to it. And so we maintain that pointer, so we're never actually losing it, of course, but it's one reason why potentially linked lists could actually be a little bit slower when you're accessing particular nodes of the list than an array. It's because the memory is not contiguous. But note, because it's not contiguous, we can add, remove nodes arbitrarily. And it's pretty easy to do so, in fact. Oh, yeah, sure. So linked lists versus arrays and vectors. So lists can grow and shrink as needed, unlike arrays, which we know have a fixed size. Even if that fixed size is not known until runtime, in other words, we could get, using cin from the user, we could get the size of the array dynamically at runtime, but once we get that, and once we create the array, we're sort of stuck. We have that array of that given size, and that's it. In order to expand the array, we have to do some funny business, like copy the contents of the old array into the new resized array, and that just gets a little bit messy. Then, unlike vectors, insertion or removal of a node in the middle of the list is very efficient. That is the good news. All we're really doing, and we'll see this in our implementation, all we're really doing when we start adding and removing nodes from linked lists is we're just adjusting pointers. We're just changing what certain nodes point to. Good news for us. Node organization. So more details on the specifics of the node piece. And you're going to see that a linked list really is a combination of two classes. We're going to have our linked list class, which is kind of the collection or the thing that ties all the nodes together. And then we have a node class. And this is what would be the definition of our node class. So a node contains data. One of our data fields may be organized as structures, objects, etc. It doesn't have to be just a single integer. It doesn't have to be just a string. It could be a player object or an enemy object. It could be anything inside of the data piece. And then a pointer that can point to another node, so we know kind of how the linked list nodes are chained together. We can have an empty list, and an empty list would be a list with no nodes. In this case, the list head is set to the null pointer. So that's kind of how you can check to see if your linked list is empty or not. Notice back here on this graphic, the list head really isn't a node per se. It's just like a pointer to the first node in the list. That's why it looks a little bit different in the graphic. We're really just saying the list head is going to be a pointer to a node. And if that pointer points to no nodes or is a null pointer, we say that that is the empty list. Okay, so C++ implementation of a linked list node requires a structure containing a pointer to a structure of the same type. This is called a self-referential data structure. We've talked about those a little bit before, where basically we have a struct called list node, and we just saw that a list node is going to contain a data portion, and it's also going to contain this pointer called next, and it's going to point to another list node. So anytime you have inside of a struct or a class a type, the same type that the class name is, that is a self-referential data structure. There's nothing wrong with this. In fact, we need this kind of functionality in our linked list. A node is going to point to another node. Okay, let's check out a hands-on. 1133. And we're dealing with listing 18.1 here, so no special includes yet anyway. We're going to be using namespace std like always. Before we even get into main, we're going to define our struct called list node, and there's my semicolon closing up the struct. I'm going to have a double in this case called value, or you could call it data, and then a list node pointer called next. And that is my general data structure for handling a list node. Okay, then inside of main, I'm going to have a list node pointer called head and assign it equal to null PTR. Okay, it's pointing to nothing basically. Now we can create a node here, so we can say head equals new list node. Notice we're using the keyword new. We're dynamically allocating this memory on the heap. We can say head arrow value equals 12.5. And then head arrow next is equal to the null PTR. So we've said that the head is going to then point to this new list node, and then the new list node is going to point to nothing. Now if we want to create another node, You can say list node pointer called second PTR equals new list node. You can say second PTR arrow value equals some other number, 14 or 13.5. Second PTR arrow next is then going to be equal to null PTR. Now, if we wanted to print the list here, we could see out first item is head arrow value, end line see out second item is head. This is kind of cool. So we have our head node, then we can refer to head's next node is called next, and then next also has a value. So this is kind of how you can chain together this arrow notation to traverse the linked list kind of node by node. There are other more efficient ways to do this, of course. If you had a linked list that had 100 nodes in it, you wouldn't want to have to do this 100 times to access a particular value of a particular node in your list. But it does kind of illustrate how these nodes are chained together using that arrow notation and pointers. And we'll end all there and return to 0. Shouldn't be any surprise what we see here. Should get a 12.5. Oh, hello. Exception was thrown, read access violation. Head.next was null PTR. I know what we did. Can you see the mistake? If you're following along with the textbook on the right here, you can see the mistake. The problem is we've got our second PTR. We've set our second PTR next equals null. The problem is we never linked up the head to the second node. Currently, these nodes are not connected. They're just existing in memory, not knowing about each other. We need to say head arrow next is equal to second PTR. And now we should get rid of that null error. Yep, 12.5, 13.5. So this is very much a manual way to wire up a linked list. We're creating nodes kind of one by one, setting their next pointers, linking them together, printing them out, traversing the linked list via the arrow notation. Again, there are much better ways to do this, but this is a good kind of first peek at a linked list implementation. All right, creating an empty list. Of course, we define a pointer for the head of the list, and it looks like that. List node pointer to a list node called head equals null PTR. The head pointer is initialized to indicate that it is an empty list. You can equip these with constructors. I don't know that we've actually seen constructors inside of struct objects before, but you can do it like so. So we've got our int, our data, our pointer to the next. Then we have a list node constructor where you can pass in an int for your data. You can pass in a pointer to a list node called p. Notice how it's using a default value here. It's going to be by default equal to the null PTR. If you don't pass in your own, that will be used by default. And then we're simply initializing here data equals d, next equals p, and we're off to the races. Building a list from a file of numbers. We're going to try to do this, I think in the next hands-on, but the idea is we've got an external file, a text file or an ASCII file, filled with some numbers, and we want to build a linked list where each node of the list represents one of those numbers in the file. So it might look something like this, where we have a pointer to a list node head equals null. We may have an int called val. Then we're going to loop through the contents of whatever that in file is, line by line, and assigning each line to val. Now we can say add nodes at the head. So we can say head equals new list node. We're going to use our constructor notation here. List node, passing in our val, passing in our head. So the assignment is right to left. The precedent value of head is used when the node is created, and then the address of the new node is assigned to the head, like this. Let's check out a hands-on here, 18.2. See if we can't make some more sense of this. 1136, right here. Good. Are we collecting? Let's see. Let's open a file. Okay, numberfile.dat. Cool. So let's fire up. Add new project. EX 18.2. Oops. Okay, so we're going to be reading from a text file, hopefully. So we're going to include fstream like so, using namespace std. We're going to create our struct list node. We'll be storing doubles here. So double value list node pointer called next. Here's our constructor. List node, we're going to pass in a double value 1 list node pointer called next. Oops. Next 1 assigned to the default value of null ptr. Value equals value 1. Next equals next 1. And we're good to go. Okay. Let us then say double number list node pointer called number list equals null ptr. Yes, let me do that. All right, if stream number file, passing in the name of the file, number file.dat. If we fail to open it, if not number file, cout couldn't open it, exit 1, some failure exit code. Otherwise, we'll keep going. Cout contents of the file are endl, and then we will enter into our while number file, saving each line into number. We're going to loop through this guy, and we'll simply cout number, some spaces in between them. And now we're going to build up our linked list. So number list equals new list node, passing in number and the head. So number list. And now we can traverse. So here we're printing out the contents of the file while we're building up our linked list. Next, we're going to cout endl. We're going to cout the contents of the list. So not the contents of the file, but the contents of the linked list, which contains data from the external file. So the contents of the list are list node. So we're going to create like this pointer to a list node, assign it equal to number list, so the head of the number list, while ptr is not equal to the null ptr. This is a good way to loop, by the way. So this pointer is going to keep moving. You can see here in the body of the while loop, the pointer is going to keep moving, pointing to the next node in the list. So this loop is going to keep going while the pointer is not equal to the null pointer. This is a very, very good way of looping through a linked list that we have structured like we do, where we know that if a linked list node is pointing to null, we know that's the final node in the list, and that's going to cause our while loop to terminate. So then we can cout ptr arrow value. And then here's our reassignment of ptr. So ptr equals ptr arrow next. Without that statement there, you can probably guess we would have an infinite loop, return 0. Okay, let's see if we can track down this data file in the resources for this chapter. Again, it's called, let's see, numberfile.dat. Let's just take a look at the structure of this file. Let's see what we're dealing with here. Ah, good. I'm glad we opened this. I said that the numbers were all stored on separate lines. They are not. They're stored on a single line with spaces separating them. 10, 20, 30, 40. So let's check out a sample run of this. I tell you what, I'm not going to copy in that file into my project. That's the source of a multitude of errors. You guys can do that if you like. Instead, we'll just assume that this runs properly. When we loop through the file, we see 10, 20, 30, 40. When we loop through the list, we're going to see 40, 30, 20, and then 10. Hopefully. Okay, numberlist.h. Let's see what we can do with numberlist.h. Is there a hands-on corresponding to this? Yes, there is. Okay, let's create a new hands-on. Console app ex 18.3. And I believe this really is just a header file. So you can add a new item, a header file, and we'll call it numberlist.h. And we'll go ahead and build this up. So now we have a numberlist.h. We're going to include IOStream, std. Now, we're actually going to build up a class called numberlist. So class numberlist. We're going to be able to use this in some more hands-on. So it's good to kind of type it out manually first, and then we'll be able to use it whenever we need it. We're going to have a protected section, and in that section, we're going to have a struct called list node. I don't know if we've actually seen this where we've had a struct as a property of a class, but you can do it just like you would do it outside of a class. So we're going to have a double value. We're going to have a list node pointer called next and a constructor. Double value 1, list node pointer called next 1 defaulted to null PTR. And now we'll do our assignment. Value equals value 1. Next equals next 1. Close up the struct. And we move on to the next property. We're going to keep a pointer to a list node called head. It's going to keep track of that for us. We're going to have a public section. We're going to have a constructor for number list. And we're going to say head defaults to the null PTR. Do need a semicolon there. Notice how we've inlined the implementation for this constructor. Nothing wrong with that. We have our destructor. If I can type it. I have a strange keyboard where the tilde key is strangely difficult to type. So there, the destructor for number list. We have a void method called add, passing in a double number. So I'm going to add a node. Void remove a node, double number. And then a void display list that is const. We will not be modifying any data inside of this method. Oh, we do have an implementation file, numberlist.cpp. Okay, so because list node does not need to be accessed by any code outside of it, we've declared it inside the numberlist class, and we've declared list node in a protected section to make it accessible to classes that might later on be derived from it. Cool. You know what I'm going to do? I'm going to copy all this. I am actually going to delete numberlist.h. I didn't realize we had that CPP file. Delete it. Now what I want to do is add a full class here. Now we can do number list. We'll get the header file. We'll get the CPP file. There it is. I'll just paste this in. Now there's nothing wrong with having implementations in your header file, as well as having a separate CPP file for that implementation. Nothing wrong with that. So we'll head over there where we've included numberlist.h. We're going to start building up our list of methods here. So we got void numberList : going to define our add method, passing in a number. If head is equal to the null PTR, so this is a special case where we basically have an empty list. We're going to say head equals new list node, passing in number. Otherwise, if it is a non-empty list, we're going to use node PTR to traverse the list. So list node pointer called node PTR equals the head, while node PTR is while node PTR's next node is not equal to null PTR. There's that familiar formula that we talked about in the last exercise that helps us traverse a linked list and determine when we've reached the end of it. While that is not true, we're going to say node PTR equals node PTR arrow next. Okay, so we're just going to keep looping. Now we've reached the end of this loop. So reading in the comment here, node PTR next is now the null pointer. So node PTR points to the last node. By the time we've made it here, we know that node PTR is pointed to the last node. So we can say node PTR arrow next is equal to a new list node passing a number. So this add method, you should be able to derive based on our implementation, adds a node to the end of the list. This pointer is traversing the linked list until it reaches the end node, the final node, and then it's creating a new one sort of at that location. That's one way to add a node to a linked list, not the only way. We're going to see later how we can add and remove nodes arbitrarily in arbitrary locations. I see add here. I don't see the remove. Here's display. Maybe that's implemented later. Okay. We have a void method numberList display list. It is const list node pointer called PTR node PTR equals head while node PTR. Basically, that's saying while it's pointing to a valid node, cout node PTR arrow value. Got a bunch of spaces. Then move on to the next node. So node PTR equals node PTR arrow next. Life is good. We should be able to display our list. Now we're going to create our destructor. So numberList, very important when you're dealing with complex data structures like this. We're using new to create new memory on the heap for every new. Remember, basically we need to have a delete. So I'm going to bring in my tilde here, my destructor for numberList. So it's going to look like this. List node pointer called node PTR equals the head while node PTR is not equal to the null PTR. We are going to create a new list node pointer called garbage equals node PTR. We're going to say node PTR equals node PTR arrow next, and then we're going to delete keyword garbage. Okay, so we're like grabbing a copy of that pointer, storing it in garbage, and then saying, all right, node pointer, move on to the next one, delete garbage, now reassign garbage to whatever node PTR is pointing to, advance that pointer to the next node, and delete garbage. So we're sort of like, we're not deleting until we know that our node PTR is pointing to the next node in the list. And this should take care of our implementation. Hopefully later on we'll be able to see the remove method. And then, yeah, we have 18.3. Good. So actually using this thing, here we are. Of course, we'll need to include number list.h. Life is good there. Now to actually use it, we can say number list. So creating this on the stack instead of the heap. We're not using the new keyword there. We are using new and delete in the implementation, but not inside of main here. So we could say list.add 2 point whatever, list.add something. How about one more? List.add, sure. Then we can say list.displaylist, open close parens, cout, endl, return 0. Let's activate it and make sure that everything runs as we would expect. And it looks like it does with my wonderful spaces separating my output. Cool. Back to the presentation. All right. Traversing a linked list. Maybe we should have done these slides before we did some of our implementation, because here we see the algorithm for moving through a linked list defined in sort of English before we actually tackled it in code. So list traversal visits each node in a linked list to display the contents, validate the data, whatever you need to do. Basic process, as we've seen, sets a pointer to the head pointer. Then while the pointer is not equal to the null pointer, do something with the data, whatever you're going to do. This is very much like up to your individual linked list implementation. But after you're done doing that, we're going to set the pointer to the successor or the next. I don't know why they don't just say next of the current node, and keep doing that until the pointer is equal to null PTR. Then we're done. Here we go. So here, node PTR, and I always like to say that this is just a pointer that's kind of sitting, hanging out outside of the linked list. It's just kind of like an observer pointing to various things in the list. But to begin with, it points to the node containing 5, then the node containing 13, then 19, and then it points to null PTR, and then we stop. So that's kind of been our approach in some of the hands-ons, was we've created this external pointer that's just kind of moving through the list, pointing to different parts of it until it reaches the end, and then we terminate our loop. So here are some basic operations. We can add a node, delete or remove, traverse it, and then delete and destroy the list. And so, of course, over here, if we had used the new keyword to dynamically allocate our number list, we'd want to use the delete keyword to destroy it. And then, of course, once we say delete list, that is the point at which our destructor would run and go through and clean it up. Creating a new node, so we have a list node pointer called PTR. We have our data called num. We say PTR equals new list node, passing in our data. And it will look something like this. So we could add an item to the end of the list. If the list is empty, we would set the head to a new node containing the item. We just saw this in the hands-on. So head equals new list node, passing in num. If it's not empty, move a pointer p from the head to the last node using a loop like this, where p is basically keeping track of nodes it's pointing to. Eventually it's going to reach the end node, then add a new node containing the item. p.next or arrow next equals new list node, passing in a num. So here, the list originally had nodes with 5 and 13. P locates the last node, then a new node with the item 23 is added. So this would be like the state of it as we are looping through. P is pointing to 13. We know that P next would be null pointer. So we can add a node to the end, and then that node, which contains 23, then points to the null pointer. Okay, there's other stuff we can do, like while we're adding items to our list, we might want to keep track, or we might want to keep the nodes in a linked list in order according to their data fields. In this case, adding a new node to the beginning or the end will not work. So a couple possibilities. You could say that the add point is at the head of the list because the item's at the head. Item at the head is already greater than the item being added, or because the list is empty, or the add point is after an existing node in a non-empty list. Let's check out this guy, sorted number list.h. Maybe we'll just do like a read-only view of this. 1144. Yeah, sorted number list.h. Let's see if I can grab that from, yes, I can. Sorted number list.h. Here's the header file. This extend, yeah, so, okay. This guy extends the number list. Let's go ahead and actually do this just so you can see that in action. Let's add a new project. We may just copy and paste it just so you can see kind of the whole process. EX. Like so. Now, because it refers to number list, I'm going to go ahead and open those as well. So we need to add that class first. So I'm going to add a class number list.h in CPP. Then I'm going to add, oops, yeah, sorted number list. And we'll just copy and paste in that code. Sorted number list. Header file and the CPP file. Very good. Let's bring in some code here. So the number list dot CPP. Number list.h. Curious if they have the add display destructor. Yeah, they never did do the remove. Number list.h. Cool. Like so. Now we'll take a look at the sorted number list.h. And the only change here is we're changing the add method. Leave that pragma in there. Notice how it extends number list. This is being included, no problem. So I think we're good to go there. And the sorted number list.cpp, which is where we'll focus on, I think. It's the new bit here. So the program illustrates number list, append, insert, and display list member functions. Right. So again, the only thing that really changes here is when we add. So when we add to a sorted number list, we're keeping two pointers here. We're keeping track of what we're currently pointing to and the previous node that we've pointed to. So again, two cases here. The case of an empty list, in which case we're going to say if the head is equal to null or head value is greater than or equal to whatever number we've passed in. Yeah, so either it is empty or the head's value is greater than or equal to the number we're passing in. A new node should go at the beginning of the list. Those two conditions are when we should create a new node at the beginning of the list. So to say head equals new list node passing in whatever value we are, and then the head. Otherwise, we're going to say that the previous node pointer is equal to the head, and the current node, I prefer to call this current node pointer, equals the head arrow next. And now we're going to have to do some looping and some logic to try to find the insertion point for this node. So we're going to say while node PTR is not equal to the null PTR, and node PTR value is less than the number, now we're going to say previous node pointer equals the current node pointer, and the current node pointer is equal to the node pointer, current node pointer arrow next. Now we can do the insertion. So this is all about finding out where we're going to put the thing. This is all about actually putting the thing there. Now, one nice thing about keeping track of a sorted number list is as you're adding things to it, you can assume that all the previous things you've added to it are already sorted. That's why we can say things like this here and this here. We can make assumptions about the data that we're inserting because we've guaranteed already that the data we're inserting has been sorted. Now, if we jump over to the implementation, we should be able to include sorted number list.h, and perhaps I can copy some of this, maybe. What is this? Listing 18.4. Over here. Like so. So it's going to be adding some values here, 2, 7, 12, 10. So it's not actually adding data here in the correct ascending order. It does kind of at the beginning, but with this guy adding 10.5, that is not in the correct order. So that's when our logic is going to kick in and hopefully add it to the correct location. Set a startup. At the end, we'll display the list. Hopefully we see, yep, 2, 7, 10, and 12 appears to be in the correct order. So that's one nice thing you can do. It kind of reminds me of how back when we were dealing with arrays, we kind of kept track of like how big the array was, so we didn't have to constantly go through and calculate it. As you're going through and doing things to your linked list or whatever data structure, you can impose like restrictions on the data structure so you can later make guarantees about how the data is laid out in that particular structure. Yep, we did 18.4. Let's check out 18.5. See what's in store for us there. Ah, yes, finally remove. Okay, so 18.5 is really just an int main with some adds. I'm guessing there'll be a remove here. Yep. Removing the value in the middle. So what you're removing basically is the data piece. So it said remove 7.9. So wherever it sees 7.9, it's going to remove that that node. Really, though, the key thing here we want to focus on is the removing an element. Yeah, we'll just look through it here. So as we would expect, so we've got a void number list remove method passing in the number that we want to remove. This is one way to do it. You could pass in the data of the list node that you want to remove, or you could optionally pass in an index of the node you want to remove. It's just up to you and how you want your linked list to work. In this case, we're passing in the data that we want to remove. So again, we're keeping track of the node pointer and a previous node pointer. If the list is empty, don't do anything. So if not head, return. You can't remove anything from an empty list. Next, we're going to determine if the first node is the one to delete. So if the head node's value is equal to the number that we want to delete, we're going to say node PTR equals head, head equals head arrow next, and then delete the node PTR. Cool. If it's not the thing that we want to delete, now we're going to initialize node PTR to point to the head, and we're going to skip nodes whose member is not our number. So while node PTR is not equal to null, and node PTR arrow value is not equal to the number that we're trying to remove. So two things here. So we're going to keep looping until one of two things happens. We're going to keep looping until either we reach the end of the list, in which case this thing will become true, or, I know this is and, but the other thing that could happen that would cause this to finish is that node PTR value does become equal to whatever number we're trying to remove. Okay? If any of those happens, then the while loop terminates. But while we are looping through, we're going to say previous node pointer equals the current node pointer. The current node pointer equals node pointer arrow next. So once we've made it through this while loop, okay, then we kind of know that we've found our insertion point, basically, or our removal point, I should say. So if node PTR, if we're done with this while loop and we still have node PTR pointing to a valid node, we know that we found the location to delete. And now we're just reassigning pointers to go ahead and delete that particular node. Then, like I say, just the implementation there. Okay. So adding a node to the head of the list. So this is kind of, again, the English discussion of our discussion in code that we just had. Never hurts to see it again, though. So we're going to test to see if the head pointer is null, or if the node value pointed at by the head is greater than the value to be inserted. You must test this in order. The results are unpredictable if the second test is attempted on an empty list. You don't know what the heck is going to happen then. Then we're going to create a new node and set its next pointer to the head, and then point. So inserting a node after the head requires 2 pointers. Pointer to locate the node with the data value greater than that of the node to be inserted, or to locate the end of the list. And we need a pointer to, like, I guess trail behind is a good way to put it, or hang back one node to point to the node before the point of insertion. We need to do that so that we can correctly link up the nodes after we've inserted it. Then the new node is inserted between the nodes pointed at by these pointers. Thank goodness we finally have a graphic. Okay, so inserting a node into a linked list. We're trying to insert number 17 into this list. So we're traversing. Now finally, node pointer is pointing to a node, the first node that is larger than the item we're going to insert. So it's now pointing to the next node after we want to insert this guy. Previous node is pointing to the node before, right before we want to insert. So you can see this guy's pointing to the before node, this guy's pointing to the after node. We need these pointers to correctly wire up 17 in the next step. And I like how this graphic looks. So previous node arrow next is going to be our new node, and then the new node's next is going to be equal to the node PTR. This is why we need to keep track of both the previous node and the next node. Graphics kind of really drive this point home here. If the code didn't make much sense when we went through it, check it out again after we've kind of talked about these graphics. To destroy it, obviously we're going to use the destructor for our linked list class. We remove all nodes used in the list. We have to traverse, visit each node. We're going to unlink. We're going to free the node's memory using delete. We're going to set the head to null PTR. We're going to park that pointer. To remove, so we're going to find the node to be removed. We're going to remove it and then delete the memory associated with the node. Again, requires 2 pointers, one to locate the node to be deleted and one to point to the node before it needs to be deleted. Kind of the same thing, but opposite. So we've got a previous node, got a node PTR. We want to locate the node containing 13. That's the one we want to delete. So previous node is pointing to the node right before the one that we want to delete. Node PTR is pointing at the one we do want to delete. Okay, so now previous node's next is going to be equal to node PTR's next. We've reassigned those pointers, and now node pointer has been deleted, and we park the node pointer to set it equal to the null PTR. Okay, so we've been talking about specific data stored in linked lists. Let's talk about making them a little bit more generic with linked list templates. So we can write a linked list template by replacing the type with a type parameter like T. If you're defining a list as a class template, then all the member functions must be function templates. In other words, they must be of type T. So the implementation assumes use with data types that support comparison, like double equals and less than or equal to. Okay, so whatever you do pass in for your concrete type T when you go to create your linked list, you must make sure that whatever those data types are support these 2 operators. And if they don't, you need to basically add that functionality. Finally, linkedlist.h on page 1150. And here it is. Full linked list template. It is a lot of code, so I think, yeah, it is just one header file though, so that's kind of nice. Let's grab linkedlist.h right here. This is all linked to within the comments of the YouTube description. Let's create a new hands-on for 18.6. There's not a ton of hands-on exercises in this chapter, but 18.6 console app. std, and we're also going to do that. Yes, we're going to, we don't have it yet, of course, but we're going to include linked list.h. So it's going to give us an error here, but no worries. We're going to add a new item header file, linked list.h. We'll paste it in. Okay, so this should more or less be a full template-based implementation of our linked list. Let's talk about some of the differences between this and kind of the implementations that we've been working with as far as the concrete data types. So of course, as you remember from the template lesson, to make a class template-based, we have to say template above the class keyword, angle brackets, and then we say class space some letter that stands in for your concrete type, and in our case we call it T. Okay, so this linked list is going to store data of type T, where T could be almost anything that supports the equals, like double equal sign. I think it was the less than or equal to. So now, instead of saying double value or int value, we say T value. In our constructor, we say T value 1. The pointers don't really change. It's just wherever we had a concrete data type before, we now have to change it to T. So we added type T called value. We remove a type T called value. The add code really doesn't change except for the signature here, which says T. Oh, I should mention, above all of your implementations, all of your method implementations, you must say template class T. That makes the methods sort of templatized as well. But the add doesn't change, the remove doesn't change, except for, of course, the template class T. Display list doesn't change, and the destructor doesn't really change. Yeah, let's see here. Where's my constructor? Right here. The destructor looked a little bit different. Yeah, the destructor, very, very subtle difference here. So the destructor, again, must be marked a template with class of type T, but in the destructor, notice how it says angle bracket with T in the middle of it. Very, very subtle difference. Don't forget that piece. But the implementation is just the same. Okay, there's a templatized version of a linked list. Now you can see here, yep, we're including linked list.h. We have, in this case, a linked list of strings. We can add strings, display them, remove, display them again. You could have a list of integers or doubles or player objects, again, so long as whatever your concrete data type is, as long as it supports double equals and less than or equals, it should work. Moving right along. All right, recursive linked list operations. So a non-empty list consists of a head of nodes, or a head node, followed by the rest of the nodes. And the rest of the nodes form a linked list. It's called the tail. This is terminology we hear more so in what are called functional programming languages, languages like F#, Haskell, OCaml. They love to talk about recursion, because they can't actually do for loops and while loops, so they have to use recursion. And when they talk about linked lists, they really care about two parts of the linked list. They care about the head as one part, and then everything else as the other part. So they have a head, which is one node, then they have the tail, which is everything after the head. Many linked list operations can be broken down into smaller problems by processing the head and then recursively operating on the tail of the list. So doing the same thing over and over again, operating on different portions of the list. Now, I don't think we're going to actually do this recursively. Yeah, but it does illustrate the idea. Let's see. So we've got IOStream, FStream. We've got our list node here. Got a function prototype that's going to determine the size of a linked list, and it's going to display it. So this isn't really a well-structured, I would say, linked list node and linked list data structure. More loose, kind of like the first couple of examples that we did. We're just kind of working with a struct. At any rate, familiar suspects here. We're opening a file, filling up the linked list with data from the file. I believe the interesting bits come from, yes, the size, and then the display list. Okay, so remember, with recursion, we need really two parts. You need a base case that's going to basically stop the recursive calls so that we don't end up with an infinite recursion. And then we need basically a call to the function that we're inside of. So let's check out the size. So in size, we're passing in a pointer to a list node. Our base case is if the pointer is equal to the null pointer. We know from previous examples that when that happens, we've reached the end of the list, so we're going to return 0. In other words, if we entered into size here right away and immediately PTR equaled the null pointer, the size of this list is 0, so we return 0. And if that were the case, we were truly working on an empty list, there would be no recursion to unwind. However, if there's a list of any meaningful size, we would return 1 plus the size of PTR's next node. And then remember that 1 plus is kind of how we do incrementing, or like plus plus or some number plus 1 when we're doing recursion. So you're saying give me 1 plus whatever the size of the rest of the list is. And we're going to keep doing that until eventually we hit the base case and we're going to return 0. The recursion unwinds and we're going to get the sum of all these 1 pluses that we would have hit earlier. Same thing here for display list. Our base case essentially is when PTR becomes the null pointer, but while it's not, print out PTR's value and then call display list of PTR's next. Kind of an interesting way to think about lists, breaking it up into two parts, the head and then everything else in the list. And number list 2 here contains recursive member functions. If you want to check that out, that's more of an organized kind of number list, or an organized linked list called number list 2. It's going to use recursion. It's going to use classes instead of kind of the loosey-goosey structs that we just talked about. Okay, so again, we began with the code here of the recursive part of linked lists. So we'll talk about the kind of the high-level English definitions now. So to find the size of the list, if the list is empty, the length is 0, which is your base case. If it's not empty, find the length of the tail and add 1 to obtain the length of the original list. Here's kind of what we just saw, passing in a pointer. My list is null, return 0. The list is empty. Otherwise, keep track of how many nodes you're recursively moving through. So 1 plus the size of whatever mylist.next is. To display the contents, again, we just talked about that. Moving right along. Other things you can do recursively. So you can add and remove things recursively. General design considerations, the base case is often when the list is empty, or when you've reached the end of your linked list. And the recursive case involves using the tail of the list i.e. the list without the head. And since the tail is one fewer entries than the list that was passed into the call, the recursion should eventually stop, because you're continuing to call the function with one fewer node than you previously called. Some variations of the linked list. So you can have something. We've just been dealing with a singly linked list, and it's kind of like a forward linked list where you're always pointing to the next node in your list. But you can have a doubly linked list where each node contains 2 pointers, so one to the next node in the list and one to the previous node. So you have a forward node pointer and a backwards node pointer. So you can traverse now forwards and backwards. If you know that you're never going to need to move backwards in your linked list, singly linked list is fine. If it makes sense for you in your implementation that you need to move forward and backward, make use of the doubly linked list. This is kind of cool. So circular linked lists, you can probably guess what is going to be going on here. So in a singly linked list, it is a singly linked list, but the last node in the list points back to the first node, not null pointer. So it kind of loops around itself. And then smart pointers. So smart pointers, you can usually use them to prevent common problems like memory leaks, deletions that are accidental, and then multiple deletions. They might not be useful when we're implementing linked lists because unique pointers cannot be used due to ownership. Shared pointers add overhead of shared groups, and then shared pointers in a circularly linked list may lead to memory leaks when trying to destroy it. I've never really found the need to use smart pointers with linked lists. Regular old pointers work just fine for me. So STL does have a list and a forward list. So sequence containers in the STL with underlying linked lists in their implementation. So the regular old list just uses an underlying doubly linked list, and then a forward list uses a singly linked list. So if you just say list in the STL, you're referring to a doubly linked. But if you want to use just a singular, forward list would be the one for you. Unlike other sequence containers, you can't go directly to an element via an index. That is important. With a vector, we could refer to an index of an item in our vector. Certainly with arrays, we can do that. But access is sequential from the first to the last element. So you really kind of have to loop through the list to find the thing that you're looking for. You cannot access linked list nodes via an index. Maybe a benefit, maybe a drawback, maybe you need to do that, maybe you don't. Let's check out 1166 as we wrap up the chapter. Oh yeah, here's some list member functions. So you can resize the list, reverse it. That's kind of handy. Get its size, you can sort it, swap elements. And yeah, 18.9 is just an example of using the list inside of the STL. So you include list, and you can do lots of list things, including using an iterator to loop through the list. A couple more notes on list and forward list containers. So the constructors, you can have a default constructor. You have 2 fill constructors, like a fill with 0 or a given value. It has the familiar copy constructors and then the range constructors. Yeah, you can use online references to learn about the small differences in member methods between the 2 containers. So that has been a whirlwind tour of the linked list data structure. We've mostly focused on creating our own implementations in C++. We created a struct-based implementation, we created a class-based implementation, and then the holy grail is the template class implementation of the linked list data structure. Coming up next time, we'll take a look at the stack data structure and the queue data structure, and I would say that those are really those are linked lists, but with more restrictions placed on them. We place restrictions on them because then we can guarantee the speed at which these data structures will run. But underlying, they still kind of use the same ideas as linked lists and vectors and other containers. So check that out next time. That'll be chapter 19. For now, though, this has been chapter 18, linked lists. Thank you.